Um, so, at the end of last week, we started talking about these two scheduling methods. We talked about earliest deadline first and rate monotonic scheduling. Um, we started to go through some examples. I just want to finish this section of the course off quickly, so I'll just run through these examples with you to help you prepare to understand how to work through these problems, and then we'll move on to the next part of the course looking at compilation. So a quick reminder of the difference between RMS and EDF. So EDF is earliest deadline first, so whichever has the closest deadline, you give that process the highest priority. Rate monotonic scheduling, you give the highest priority to the one that has the smallest period or gap between times that you have to run the process. Okay, so looking at this example, where I have EDF and three processes, process 1 with an execution time of 1, process 2 with an execution time of 1, and process 3 with an execution of time of 2. Periods of 3, 4, and 5. So how would I run, check whether I can schedule this using each method? So the first thing you do when you write these examples is looking over a period of time, so these are in terms of ticks or, ticks. What you want to say is, first fill in the deadline column. So you know the process 1 has a period of 3, so every 3 you put in process 1 as a deadline. You repeat with process 2. Process 2 has a deadline of 4, a period of 4, so it's at 3, 8, 12 ticks after. So you put on all the deadlines. Okay, and same with 3. So now running through the examples, it should actually be pretty straightforward. So if I want to start off, say, with earliest deadline first, what process do I run first? Anybody? One. Process 1 has the earliest deadline, so I run process 1. What do I do next? 2. Process 2. I finish with process 1, it needs one time period. So then I can run process 2, and then process 2 is done, so then I can run process 3. Okay, what do I do at this time instant now? I run process 3. Process 3 needs 2 time periods to finish. Okay, now what do I do? Process 1, because process 1 is now available. And process 1, and it's the next earliest deadline. And this is really straightforward to follow. You should be able to do this in your own time, and you should practice this in your own time. These slides highlight just what I've shown you here. Might look a bit small on the projector. It highlights a few things that you can't schedule P1 at this instant. And the reason you can't schedule P1 in this instant is because P1's already run within this time period, so it's not available again until after the next deadline. Okay, and you can work through this and confirm this yourself. Let's go back and repeat this process with RMS. So the easiest way, or how I recommend doing with RMS, is just look at the deadlines and then fill in the processes accordingly. So I know process 1 is my highest priority process, and it will always be my highest priority process. So whenever it's available, I write in P1. So P1 is available here. Next period, I write in P1. Next period, I write in P1. So you can just copy this straight from the deadlines. Okay, process 2. Now again, I want to run process 2 whenever it's available. So process 2, I put in here. Process 2, I put in here. And process 2. So on and so forth. Then process 3, fill in the gaps. Process 3 goes here and here. So is there any problem with what I've written so far? Yeah, process 3 needs to run for 2 periods, but you see it's only run once in this slot, and then it runs again this slot. It's missed my deadline here. And this is just to highlight that RMS is unable to schedule it. I haven't done anything wrong, but RMS can't schedule this problem. So these are things that you can practice in your own time, and there's a million past papers with examples to follow this, should you wish to do this practice. Okay, assuming I have scheduling problems, just quickly, how can I solve the problem? Well, you can change your deadlines. So you simplify the problem, which is a simple solution, but quite often you can't change your deadlines. You can make some processes use less execution time, so you simplify them, look at your code, change your code a bit maybe. Employ a faster CPU or chuck it on an hardware accelerator, a GPU, an FPGA, or a multi-core CPU. So basically, it's not an easy problem when you've got a scheduling problem. You either need more processing power or to simplify your problem. There's no shortcut. Okay, priority inversion we talked about. Data dependencies, it's worth noting, data dependencies can muck up any scheduler. Note that in all this RMS and EDF, we haven't considered that process 1 needs to complete before process 2 can start. So this is just our simplified model, and obviously if you want to perform an analysis with this kind of dependency, you need a more sophisticated analysis. While I'm here, how do I create this dependency? How, in a real-time system, would I ensure that P1 has to finish before P2 can begin? Yeah. So if I put right at the start of P2, sempend, and at the end of P1 I put in sempost, then P1 will finish at say, go run P2. Also, when you're thinking of schedulers, we've talked about it a bit before, about context switching actually takes some time itself, so you might need some extra time to take that into consideration. And similarly, interrupts can take some time. So this would be your context switching time taking of your overall processing time. So if you're running near 100%, you might not actually be able to meet all of your deadlines. Similarly, interrupts could shorten the amount of space you have available to do work or processing again. So if you're running near 100%, even though theoretically it can run, in practice you might not be able to run. Okay, the rest of all this stuff is not really examinable. Talks about different scheduling techniques on Linux and passing messages in different operating systems. And we're running a bit behind on the lectures, so I'm just going to skip all this. So if you wanted to learn more about it, you can either speak to me or you can look at previous year's lectures. Okay, so now we wanted to talk about compilation. So why do we care about compilation? Well, this is how we actually run our code. So how do we go from C code to actually running it on a machine? And we'll talk about the various steps. And in terms of embedded systems, or what we want to think about when I'm going through all of this, is to we really care about efficiency. So if we can save a register, if we can avoid storing work using memory, then that's actually going to make our system a lot faster. And in embedded systems, it's a lot more important than in other general software systems. So computer scientists might say, you saved a few kilobits, who gives a crap? You know, memory's cheap, who cares? But if you're talking embedded systems, large companies might care about saving you 5 cents on a device when they produce millions of them, or 10 cents here or there. Every little bit will add up. So we do care about optimizing wherever possible. Okay, so first up, let's talk about design patterns. So design patterns are a generalized description of a certain type of program. And the designer fills in details to customize the pattern to a particular programming problem. What is this all saying? To me, this is saying something very simple, which is when you code, use Google. Someone else has written something similar to you before in your life. Make use of their pre-made design and edit it a little bit rather than reinventing the wheel. And I recommend this, and therefore in this lab test coming up, unlike previous years, I'm going to make a completely open book. You can use Google. You can use whatever you want. The only thing you cannot use is Skype, Messenger, something like that. Speaking of the lab test, we've had a few people coming up to me asking what it's going to be. So I thought I'd make this fun and give you all an advantage for having attended the lecture. We're going to have a vote on whether we want it on the first half of the course, the interrupts, polling, etc., or you want the lab test on to do with the real-time systems and this kind of stuff. Think carefully. This is your opportunity. Okay, I'll give you 30 seconds to think. Okay, time's up, people. Voting time. Hands up who wants it on polling, interrupts, all of this part of the course. Okay, I count 18. Who wants it on real-time systems and this kind of stuff? We have a winner. The lab test will be on something to do with real-time systems. Now, isn't that fun? Right. Carrying on. Carrying on. So, examples of design patterns, just really quickly. I don't want to labor this because this is really to do with other courses. A simple example of a design pattern is a state machine. We all know the concept of a state machine. We can reuse it in many different ways. You can use it to parse user input, respond to various stimuli. You've practiced various methods. You've written state machines in 2072. You've probably written it in some of your labs in even this course in some form or another. This is an example of a state machine which monitors whether to have that annoying alarm on a seatbelt when someone's not sitting down and you've put a box on the seat. So how does it work? Well, you've got 4 states. It's either doing nothing, idle, someone or some box is seated. That person can either be belted or we can have a buzzer that's going off. And you can see all these states. And you could imagine if someone sits down, then we go into a seated state. If someone puts on their belt, then that person is belted. Very easy to construct a state machine. and putting on my digital logic hat, the only thing I really want to remind you here is to note that this state machine has used don't cares throughout all of their work. Otherwise, we can have the system going into unwanted states. But yes, you can easily edit a state machine to do something that you desire. Okay, this is slightly interesting. So I've got a C implementation of my state machine. We've got a couple of definitions, a switch statement which switches between the states and does various operations if you're in a given state. All straightforward, couple of questions. Constant define is better. Why? That's for the C coders out there. It's basically to do with type checking. You can check that it's an integer type, or a compiler can do that for you just to avoid any errors. In digital logic, so you should be aware, how we have is the clock switching the state. So every clock period we might check the state, go to the next state accordingly. So in software, what is the trigger? Can anyone suggest what the trigger is? Interrupt? So yeah, so all of it's kind of true what you've said. You could have it basically on the clock. Every clock cycle, software still has a clock. Operations are hitting every time. When the program counter goes around, it's going to quickly go around this state. But more useful would be having some interrupt saying switch. You don't want to change the state every cycle or constantly check. You want to check every 10 seconds or something. In which case you could have a regular timer interrupt, just like you've done in the earlier lab sessions. Okay, a second design pattern example is this idea of a circular buffer. And this is a very confusing slide, but it's okay, because the idea is very simple. A circular buffer is a software version of a first-in, first-out buffer. So imagine I have my data coming in, x1, then x2, then x3, then x4. How does this fill in my buffer? Well, first I put x1 into the first portion of my buffer, then I put x2 into my second, x3 into my third, x4 into my fourth. Then as x5 comes in, I've run out of space into my buffer, so where do I put it? Well, like I said, it's kind of like a first-in, first-out buffer. So the first in was my x1, so I'm going to replace x1 with my x5, and then x2 with my x6, and so on and so forth. Can anyone suggest why I want to do this with a circular buffer and not a first-in, first-out buffer, if I'm talking software? So a first-in, first-out buffer is a very easy concept to think about in hardware. If I was to draw out this same diagram, it would be x1, then I'd have x2, then x1, then x3, x2, x1, and I'm pushing it through my system. So I can carry on, x4, x2, x1, x3, x2, x1, and then x5, x4, x3, x2, and x1 has already been shunted out. So the reason you do this in hardware is because we can have simple shift registers which have, you can move this to the next location in memory at the same time as loading in a value. In software you can't easily do that, but if you just change your memory address location, then you don't have to. So it's just a different way of looking at the same problem. Okay, how would you use a circular buffer? This is what I consider to be horribly confusing code, and I don't suggest you look at this too much. If I wanted to implement this, let's just make this clear. If I wanted to implement this circuit, first of all, I would write software that has the same notation as my diagram. And something like this statement should never exist. For the record, if I was to do it, then I would have a simple, more of a for loop. I equals 1, I is less than n, I plus plus, y equals ai times by x I. Or this could be maybe my buffer. So that would, you could imagine that this code would implement this function together. How do I fill my buffer? Well, I would have my buffer at some index is equal to x, which is my input, and my index. To create a circular buffer, I would say this is a much simpler way. Index, increment my index, and do that modulo n, the size of my buffer. I think this code is much more clear than something like that. But anyway, again, reuse code is just all this section of the lecture is trying to cover. What we really want to show in this lecture is the whole process of going from high-level language, which can be C, Java, etc., all the way down to putting it finally onto my chip. Now, I'm most interested on the compilation phase, so I'm going to focus a lot on this, and that's how do you put it simple C code into efficient assembly language as opposed to just any assembly language. Note that you will typically have multiple C files, and this will create multiple assembly files. Anyone, why would I do that? Why do I have multiple C files? Because everyone in this room is a good coder and doesn't create a big, giant, long C file, is the correct answer to this question, yes? And yes, also we have libraries which we add in later. So you should make use of linked lists, or rather standard functions, or libraries. The final process, executing and loading on a chip, we're not really going to cover much detail. We're going to cover assembling in a later lecture of how you group all of these assembly files and link them with our libraries. Okay, so how are we going to do this compilation process? Well, we're not going to work with source code, or a computer doesn't work with source code. Why don't they work with source code? Because we don't trust programmers. Programmers write things in ways that are legible, not necessarily efficient. So a compiler, what it does is it takes the program and puts it into some form of intermediate representation, which we're going to look at control data flow graphs as an intermediate representation. Within this intermediate representation, it can play around with the data, change its order, and allow us to do more interesting optimizations. So what is a control flow data flow graph? Well, let's first look at what a data flow graph is. And the idea is that we're just representing data where we have data coming in, data coming out, and we do various arithmetic operations in between. Easier seen with examples, which is what we have here. So data flow graph, we have inputs into nodes, which we do operations. Walking from top to bottom, we have inputs to outputs. There's no control flow, no if statements, no something like this. It's just straightforward data flow graphs. So how would we work with this as a compiler? Right. The first thing they do is they rewrite it into this single static assignment form. And the idea is that we give a different named variable for every different named object, for every assignment. Why do we do this? Because it allows us to manipulate the order of our assignments much more easily. If we store this temporarily in y1, then we might be able to store this to memory or use it elsewhere, or reorder our registers. So let's give an example using this example right here of why I would want to reorder. So imagine hypothetically that all of my input variables are stored somewhere in memory, and my output variables I want to store in memory, and I want to do all the work in between. So how do I write this out in assembly language? So if I follow this code directly, I would say something like R0 is load A, R1 load B. Then I work at X, so R0 is equal to R0 plus R1. Note that I reuse R0, trying to be efficient. So if I remember roughly, R0 holds X. Okay, carrying on. Y is equal to C minus D. So R2, because I still need B, is equal to load C. R3 is equal to load D. And then I can say R2 is equal to R2 plus R3. And that holds Y. Everyone follow me so far? Okay. How do I finish this off? So I want Z. So Z is going to be X times Y. So R0 equals R0 times by Y, R2. That gives me Z. Then I might say store R0 to Z. I'm going to store my memory. Then I need to work out Y1. So then I say Y1. So Y1 is B plus D. So I already have B, I already have D. So R1 is equal to R1 plus R3. And then I store R1, which is Y1, to memory, location Y1. Okay. Hopefully you can all follow that. So what could be a potential problem here is, imagine I only actually had 3 available working registers, which might be the case on my embedded system because I want very small hardware. Okay, so I've only got 3 registers available, but you know, I've used 4. I've got R0, R1, R2, and R3 all used. So how do I get around this problem? Yeah, so I store and load words. Okay, so any suggestions? What should I store? No ideas? X. Yeah, so you could store X at this point and then load it at this point. Gets a bit messy. If you're careful, I think you can get away with just storing one variable. But by reordering the operations, you can get rid of this problem entirely. Can anyone think of a way that I would possibly reorder? I'll give you a minute. We have a suggestion. Yeah. No, there's no reason why I can't do y1 earlier. So how would this work? So I could say, I might start off the same. R0 equals load A, R1 equals load B, R0 is equal to R0 plus R1. Then I might continue to say, well, I've already got B in memory, let's load D. So R2 is equal to load D. Then I can say, I'm not going to need B again after this operation. So I could say R1 is equal to R1 plus R2. And then I could store R1 to the memory location Y1. So now I just have X stored in R0 and 2 free registers. What does that mean? So then I can say R1 is equal to load C. I've already got D in memory, so then I can say R1 is equal to R1 minus R2, and that would be Y. And then I can say R0 is equal to R0 times by R1, which gives me Z. And then I finally store R0 to Z. So the point is, what I've managed to avoid is some load or store. Now, how often will this occur? You say, how often do I only have 3 registers in my software system? And the answer is, very rarely do you have only 3 registers. But very commonly, you only have 13 registers. And very commonly, you have much more complicated algorithms than we do here. So by putting into this form, rearranging our operations into using compiler to reorder our operations and save loads and stores, note that loads and stores are very high execution time because we have to go all the way to memory and back. If we reduce the amount that we have, we're going to have a much faster program. And these are the kind of ideas that you put in compiler optimization. So this highlights how we could swap order of operations. I find this a bit confusing because actually we could put B plus D earlier as we've just seen. But yeah, we can play around the order, and having this static assignment form makes it easier. Why does it make it easier? It makes it easier for examples like this. Note that this R equals A plus B minus C has an implied order. Once you convert this to single status assignment form, you would have, say, R1 is equal to A plus B, R2 is equal to R1 minus C. You can actually write it different ways, but you can put it into this form, and if you write out this problem, you'll note that we can actually move, say, this variable earlier. We can't move this one much. Anyone, can I say why I can't move this line much at all? If this goes here, then this line is ignored. So all this is highlight. You can run through this in your own time, put this in SSA, single assignment form, and create a data flow graph just for practice. Again, lots of problems to practice on if you want to on the website. Okay, what's a control data flow graph? We talked about data flow graphs. How do we have this more useful idea of control data flow graphs? It's exactly the same thing, it's just we throw in control concepts. And we simplify data flow graphs to nodes within our control data flow graph. So, anyone, you should be able to, what is my C statement for this? If this one, switch, easy enough. This one, for, the giveaway is this. And this one, wow. Right. Easy enough, and you can imagine how you quickly build control data flow graphs. And this is an example of the process. Okay. So what's our compilation strategy? How do we go from source code to assembly plus optimization, which is what we're going to spend a while on in the next few lectures. Speaking of which, just by chance, when people compile software code, whoever uses GCC minus 0, 1, 2, or 3? Is anyone even aware of their existence? One person. So you can type in, for your standard compiler GCSE, you can have optimization 1, optimization 2, optimization 3. They will apply more and more of the techniques that we talk about here to create smaller and more efficient code, and it just takes longer to run. Now actually, if you ever type them in, probably on anything that you write, it will make no difference in terms of compilation time, but it will actually make them slightly faster. Just interesting to know. And yes, the compiler just determines your quality of code. So the use of registers, cores, so this is what we just talked about now with the simple data flow graph optimization. And similarly, reducing the amount of accesses to memory. It also has this effect on looking at your code size. Now this is often something that you'll care a lot less about, but it's worth keeping in mind that generally you have to trade. Slightly more efficient code might often be slightly longer code. Okay, the general compilation phase. We started off with this high-level language. We parse our input, so this is just reading, extracting from your code, what are your variables, what are your arithmetic operations. And you create a so-called symbol table, which has all of your variables, all of your constants, branches, etc., which allows the compiler to match the two up and play around with it, is the idea. We do lots of optimizations, independent and then dependent optimizations, and eventually get your assembly code. Right. I just broke this up because I was having problems with my computer. Right. So how do we get source code from some intermediate representation such as a CDFG, and how do we optimize it? So a simple example. How do I go from my code, my data flow graph, and create some kind of assembly code? We walked through the graph in post order. See the ECU 2071. I haven't taken out 2071. You guys have. What does post order mean? No idea. No. All right. Let's all go. Work this out. Right. Post order. We're trying to walk backwards through the tree is all we're trying to say. So you should be familiar with this, but anyway, how do you get this? Work from the bottom of the tree, work back up. So I've got Z. Z relies on W and Y. Okay, so I'm going to go back up this tree and say, does this depend only on inputs? If it only depends on inputs, then I can start writing my assembly code, otherwise I've got to delve a bit further back. So W depends only on A and B, which are going to be stored in memory or inputs. So we can start translating this into NEOS code, which is load into R3 something 16 from the frame pointer, which presumably is A. Similarly, load B, compute their multiplication, store this in register R3, and this is presumably W. Okay, now I go back here, trying my other branch. Okay, does this node only depend on inputs? No, it depends on something further up the chain, so I go further up the chain. Go up to the top of the chain. Does this only depend on inputs? Yes, it does. So then I can start writing out my code. Again, presumably this is C, load 8 from the frame pointer, load minus 4 from the frame pointer, do a subtraction, and this will get me X. Right. How come I've reused R2 there? Or why have I not used R3 there? We're done with B, so we've got R2 free, so we can reuse it. We're not done with R3, which holds W. So we can reuse register 2, we can't reuse register 4. Right. So then you can carry on. The next instruction going back down the tree, or I'm multiplying R2 by 5, which is X by 5, and then continue down the tree, and I multiply Y by W. And then I have all of my registers free again. It's a simple way of a one-pass going up and down a tree. Typically, in compilers, as you have more and more optimizations, they'll use multiple passes. And I would love to give a course on this, but there is not time in a single lecture. Just to cover control data flow graphs, same idea, but we just an example of how to translate this into assembly. If we've got our control decision to make, then we have to translate this into assembly first and write the corresponding code. So this control decision compares A plus B to 0. So we load A, load B, compute their addition. So that's our result stored in R2, and we compare if it's less than 1, which is a very confusing way of working out if something is greater than 0. So the The reason, can anyone suggest why they could be equivalent? No? Nothing? Someone? Yeah, so this assumes integer. I don't know why this is not, it would be equivalent to say compare greater than R2, R2, 0 if you wanted to. Okay, branch if not equal to 0. So this corresponds to branch if R2 is not equal to 0, I go to here. If it is equal to 0, I carry on. Okay, what is my code? Branch if not equal to 0, I'm moving R2 into 7. So this, you can see, matches this code. So R into 7, store R2, otherwise I put 5 into R2 or X and store that. The reason why you have this form of branch if not equal as opposed to branch if equal, you could muck around in either way, but quite often you try and get the true path to follow immediately after your comparison, because generally you go through the true path more often than you go through the false path when you're writing assembly code. Right. I think we'll stop here and carry on tomorrow.